Good morning to everyone. I am your Professor Malik Neri. I was your instructor in the last lesson and I will continue the lesson today. Last time we talked about double integrals over rectangular regions as well as double integrals over regions of type 1. And we have shown that we can use the double integral to give us the volume of a solid. We will continue the discussion for regions of type 2. So I will again stop the video for storage purposes. So recall, if we have a function small f that is continuous on a closed and bounded region R, if this region R is not a rectangular region, then what we did was to construct a larger rectangular region D that completely encloses R. And we define a function big F to be equal to the function small f at all points in the region R. And big F is equal to 0 at all points outside the region R, but inside the region D. So we would say that big F vanishes outside R, but still inside the region D. Then we defined our double integral of f over the region R to be the double integral of big F over the region D. If in particular our region R is a type 1 region, so recall that a type 1 region will have scalar bounds on x, so x is from a to b, but the y is bounded below by a function g sub 1 of x and above by a function g sub 2 of x. Then we have this result that the double integral of f over the region R is the double iterated integral. So the outer integral is from a to b with respect to x, and the inner integral is from g sub 1 of x to g sub 2 of x with respect to y. To determine the limits of the inner integral, we use a vertical strip inside the region R, and the lower boundary of the vertical strip corresponds to the lower limit of the inner integral, and the upper boundary of the vertical strip corresponds to the upper limit of the inner integral. So the function below is our lower limit, and the function above is the upper limit of the inner integral. Now we consider regions of type 2. So a region is of type 2 if it lies between two curves x equals h sub 1 of y and x equals h sub 2 of y, and these curves are continuous. That is, the region R will have scalar bounds on y, so y is between c and d, but x is between the two curves h sub 1 of y and h sub 2 of y. So for instance, we can consider these illustrations here. So the left one here, very clearly you have a function h sub 1 on the left and a function h sub 2 of y on the right. Now we can also have one continuous function like this parabola here, and still we can consider this to be of type 2. So the left branch of the parabola is the leftmost function h sub 1, and the right branch is the rightmost function h sub 2. Sometimes it is also possible that the bounds on y is not explicitly given. So for that, we need to get the intersections of the two curves, and from there we can determine the range for y. If we have a region R of type 2 and our function f is continuous on this region, then we can define the double integral of f over R to be the double iterated integral, where the outer integral from c to d is with respect to y, And the inner integral from h sub 1 of y to h sub 2 of y is with respect to x. To help us determine these limits, we can draw a horizontal strip inside R. The leftmost boundary of the strip is our lower limit, and the rightmost boundary of the strip is the upper limit of the integral. So the leftmost function is the lower limit, the rightmost function is the upper limit. For example, let's evaluate this double integral where R is enclosed by these two parabolas. This was similar. This is our example in the previous lecture where we consider the region R as a type 1 region. But take note, we can also consider region R as a type 2 region. And we have a leftmost function given by x equals y squared and the rightmost function given by y equals x squared. So if we are using horizontal strips, then we need to determine the lower limit and the upper limit of the inner integral, and that will be with respect to x. Okay, so we must have a lower limit, x equals something. In that case, it's automatically x equals y squared. For the upper limit, the rightmost, we must have x equals something. So coming from y equals x squared, we solve for x, and we get x equals plus or minus square root of y. Now, since we are in the first quadrant, we consider x to be the positive square root of y. So the lower limit is y squared, the upper is square root of y. And then if you get the intersections are the origin and the point 1, 1. So the value of y is 0 and 1. So the outer integral is from 0 to 1 with respect to y. To evaluate this, we first go to the inner integral. So with respect to x, we evaluate from y squared to the square root of y, and we get this expression here. Simplifying, and then integrating now with respect to y, evaluating from 0 to 1, we get 3 over 20. Okay, so this gives us the value of the double integral of 2x minus y over the region R using horizontal strips. Another example, let us determine the volume of this tetrahedron bounded by x plus y plus z equals 1. So take note that in the first octant, we can consider our function f of xy equals z to be 1 minus x minus y. So this came from the given equation here. So this will be our tetrahedron. So it is bounded by the coordinate planes and by the given plane z. Okay, now what is the base region? So the base region can be determined by setting your z to 0 because our base is the xy plane, z equals 0, so you get x plus y plus 0 equals 1, or simply x plus y equals 1. We can consider this region to be of type 1. And so the volume is given by the double integral of 1 minus x minus y over the region R. And we can consider the inner integral. So your y is from the lower boundary of the vertical strip, that is y equals 0, up to the upper boundary of the vertical strip, that is y equals 1 minus x. For the bound on x, we just get the intersection of the line with respect to the y-axis and the x-axis. So with respect to the y-axis, the intersection is at 0, 1. So x is 0 there. And on the x-axis, the intersection is at 1, 0. X is 1 there. So the region has x from 0 to 1. So this is our double iterated integral, and evaluating the inner integral with respect to y from 0 to 1 minus x. So evaluating that, we simplify, and then we integrate with respect to x, evaluated from 0 to 1. And the answer here is 1 over 6. So the volume of the tetrahedron is 1 over 6 cubic units. Now let us give a summary of some properties of the double integral. Recall that we already presented two properties of the double integral in our first lecture, and the double integral satisfies linearity conditions. We add a third one, and the third one is this. Suppose that the region R can be partitioned into two subregions, R1 and R2, so that these two subregions do not overlap. Then the double integral of f over r is equal to the double integral of f over r1 plus the double integral of f over r2. So we can evaluate the double integral separately, and to get the value over the entire region, we just add up. So to illustrate that, let's consider this example where the region R is enclosed by the parabola y equals x squared. We have the cubic x equals y cubed, and the line x plus y equals 2. So this will be the region here. Now to evaluate the double integral, we can consider the region to be of type 1. So, but then we can see that this region can be partitioned into two subregions. So you have R sub 1 on the left. So this is to the left of the y-axis, and R sub 2 on the right of the y-axis. So how do you determine these subregions? You just get the points of intersection. Okay, so we have an intersection at negative 2, 4, and the intersection of the parabola with the cubic is at the origin here, and the intersection of the cubic with the line is at 1, 1. Okay, so we can divide this into regions R1 and R2, and each is of type 1. So hence, the double integral over R is just the double integral over R1 plus the double integral over R2. So for the iterated integrals, let's consider for R1, the outer integral will be with respect to x. And for R1, the value of x is from negative 2 up to 0. And for R2, it is from 0 to 1. Okay, so negative 2 to 0 and 0 to 1. Now, what will be the inner integral with respect to y? So we take a vertical strip for R1. The lower boundary will be y equals x squared. The upper boundary will be y equals 2, 2 minus x. So please correct this. This should be 2 there. So you get a 2 minus x. And then for the second region, the lower boundary of the vertical strip is y equals a function of x, but this is now the cubic x equals y cubed. So we take the cube root. So we get y equals the cube root of x as the lower limit, and the upper limit is y equals 2 minus x. Okay, so let's evaluate for the first region R1 here. This is our integral, and we evaluate the inner with respect to y. We get 2xy from x squared to 2 minus x. We simplify this and then evaluate with respect to x. From negative 2 to 0, we simplify, we get negative 16 over 3. Now for r sub 2, the double iterated integral is this. Evaluate the inner integral with respect to y from the cube root of x to 2 minus x, and then simplify that. Next, we integrate with respect to x from 0 to 1, and this gives us 10 over 21. Then the integral of the double integral of 2x over the entire region R is just the sum of the two iterated integrals. And that gives us negative 34 over 7. Okay, so let's take note of that, negative 34 over 7. Now, what if we treated the region R as a type 2 region? That is also possible. So if you treat R as a type 2 region, then we will be using horizontal strips. And notice that we can partition the region R into two subregions. The first subregion R sub 1 will be from the origin up to the point or up to the line where y is equal to 1. And then the next subregion R sub 2 will be from the line y equals 1 up to the point where y is equal to 4. Okay? So the double integral now of 2x over r is the sum of the double integrals of 2x over r1 and 2x over r2. So specifically, take note that the outer integral now will be with respect to y, because the y value is from one scalar to another scalar. So for the region 1, the y value is from 0 to 1. And for region 2, it is from 1 to 4. Okay? Next is we want to know the inner integral. So for the first region, we draw a horizontal strip. The leftmost boundary would be x equals something. This is in the parabola y equals x squared, so we get the square root. So x is equal to plus or minus the square root of y. Now, what will be the sign? Since this is in the second quadrant, x is negative there. So we take the negative square root. So x is negative square root of y as the lower limit. And the upper limit is x equals y cubed. Okay, so we get negative square root of y up to y cubed. For region 2, the lower limit is still x equals negative square root of y, and the upper is x equals 2 minus y. Okay, and then we evaluate each integral. So with the inner integral is with respect to x, so we get x squared from negative square root of y to y cubed. And then simplifying this, we evaluate now with respect to, we integrate with respect to y. Evaluated from 0 to 1, and the value is negative 5 over 14. For region R sub 2, we evaluate the inner integral with respect to x, evaluated from negative square root of y to 2 minus y. Then we simplify. Then we integrate with respect to y, evaluated from 1 to 4. We simplify, and we get negative 9 over 2. So therefore, the double integral of 2x over r is the sum of these two iterated integrals, and this sum is negative 34 over 7. Exactly the same as the value we obtained when we considered the region to be of type 1. And that's what we expect to have because we are dealing with the same region anyway.